Okay, thank you, Mahapatra sir, for the introduction, and I welcome you all in today's lecture. So, as introduced, today I am going to talk on thermal comfort in built environment. So, the title itself, you you must be aware of just the meaning of it. This thermal comfort means thermally how much we are comfortable, and built environment means whatever we built, the environment that we built, we create. It may be enclosed, it may be semi-enclosed. So all the environments that are created by human being. So today I will cover about thermal comfort and its importance. So why we need to study in thermal comfort, and then what are the challenges associated with it, and little bit of science behind it. And then after that, I will discuss a glimpse of the work that I have done so far, that is in India and Europe and in some different kinds of built environment. And then uh, at the end, I will talk about future of the thermal comfort research. So let's start with thermal comfort. So thermal comfort, why it is important? Because we spent about 95% of our lifetime in the built environment and just 5% outside. So the more we spend time inside the built environment, it may be houses, it may be offices, it may be inside buses or cars, or maybe recreational centers like shopping malls, cinema halls. So all different kind of built environment, all together, it constitutes about 95% of our lifetime. So it's quite huge. So if we spend so much time in such environment, it becomes very important that we must feel thermally comfortable. And whatever the thermal comfort we achieve there, it may be substantial, and we must be like accepting towards it. And the cost of achieving thermal comfort is very high, because generally in today's perspective, we use air conditioners. Simply we use air conditioners, and we know, as we are a student of energy, we know that what is the energy cost of running an air conditioner. And then also it is very important because it affects our well-being, our health, our learning ability, our productivity, and above all, it is related to the emissions, CO2 emissions, as we know. And it is also indirectly related to the global warming. So if we disregard this thermal comfort in the built environment, as I have just discussed, uh, we will use more air conditioner. If we use more air conditioner, we'll use more energy, and more energy use means more CO2 emissions, and it will lead to global warming and climate change. So our main emphasis is to lower this, lower the use of air conditioner, lower the use of energy use, and subsequently lower the impact of global warming and climate change. So what are the challenges? So it's the challenge is associated with this thermal comfort is lies in the definition itself. So there is definition by Asray as like thermal comfort is the condition of mind that expresses satisfaction with thermal environment. So it's just a state of mind. It defines it, and it also, in the other hand, is also says that people or the occupant who are staying in the built environment are just passive, passive to this thermal comfort. They doesn't react. whatever we provide it, they accept it. But this was not an accurate, definition. So then there was a modification done in this definition in starting of the 90s, and the pioneering work was done by Professor Richard Didier, Professor Nicole, Gail Brazier, and so many other scientists. They did some path-breaking work, and where they said that actually people are active in the thermal environment, and when they feel discomfort, they react in a way which tends to restore their comfort. And this is more agreeable definition, as we experience also. Whenever we feel discomfort in the built environment, we always act, and we act in a way that restores our comfort. So this was the definition, and it is called adaptive thermal comfort. Means as people adapt, uh, uh, through their reactions to the environment. And above definition, it also points that if a enclosed environment has a large number of people, then each people have their different psychological and physiological experience. So they may respond differently to the same environment. So it becomes really a challenge to bring everything to a conclusion where we can point a single or a range of comfort variables. And there also lies a challenge where we have to convert all these qualitative responses to quantitative values, and there involves a lot of statistical analysis. So to converge all these subjective responses to quantitative values, we have to record the thermal sensation now and preferences now. So if we record thermal sensation and occupants preferences, it becomes somewhat easy to converge the values. So in thermal comfort research, actually there are 4 environmental parameters and 2 personal parameters. So 4 environmental parameters, that is air temperature, relative humidity, air speed. This air speed is not the actual air speed, but this it is across our skin. So the air speed that is across our exposed skin, so that we call it air speed. And then radiant conditions, that is we consider mean radiant temperature for the calculation. And these factors are environmental factors because we as a design engineer, we have to control these things. And then the personal factors are clothing and activity level. These are actually person dependent. So each person, based on their choice, they wear clothing, and based on his need, he do different activities that is related to metabolic rate, directly related to metabolic rate. And metabolic rate is directly related to heat produced from the body. So these are personal, person to person. This varies person to person. And also the mental state of the subject. If it is very anxious, or is in very the person is very excited, then definitely his metabolic rate will be higher, and that's also affects his response to the thermal environment. So that we also have to take care. And as a design engineer for built environment, a person who is working as a consultant or as an expert of this subject, he should have a very good understanding of this. So this is a designer's and engineer's job. He has to understand physical basis of thermal comfort and related variables, appreciate the influence of psychological aspects of thermal comfort, use of this understanding and appreciation to design spaces that building users will decide are thermally comfortable. So these are some of the instruments that we use. These are portable instruments that we can carry. So as we know that this is the subject where we need to interact with the occupants. And so the occupants may be in different types of built environment. So if the instruments are very bulky, it's very difficult to carry. So generally and most often we use portable and very sensitive instruments. So we have to carry, we have to interact with the occupants, and while we are interacting, we have to record the physical parameters like temperature. We also record globe temperature, we also record air velocity, humidity, and surface temperatures, and so on. And when we put all these instruments in one stand, we also call it a weather station. So generally we keep this close to the occupants with whom we are interacting and collecting the data. These are the different kind of setups, experimental setups, where we record the responses of occupants. The top left figure is of climate chamber, where the external environment are controlled, and then people are indulged in different types of activity, and we record their responses. Next one is this a classroom setup. There also experiments are done. And then we also do some experiments in cars. And in the bottom right hand side, you see this all the instruments, they are on trolley, and we just carry this to the occupants with whom we are interacting. So when we carry out this comfort service and we interact with the occupants, we generally ask them to vote on thermal sensation scale. That is a 7-point scale, and its range starts from -3 to +3. It's -3 stands for cold and 3 stands for hot. As you see in the figure, 0 stands for neutral. So neutral means you are comfortable, and at that activity level, that clothing, and doing that work. So on this scale, people used to vote, and we record their thermal sensation. There are also preference scale on similar 7-point thermal preference scale. So we record those votes also, and then we analyze. So these are some of the conditions for environmental measurements. So if the person is sitting, we have to carry out 3 measurements, that is at 0.1 meter, that is 10 centimeter at the ankle height, then 0.6 meter, that is at the waist height or at the level of chair, and then 1.1 meter, that's the height of the neck. Same measurement is done when the person is standing. So just the heights will change. So if the person is standing, generally his waist height is 1.1 meter. And if the person is standing, generally his neck height is 1.5 to 1.7 meter. It's depend upon where you are doing the experiment. If you are doing experiment in European countries, generally the height of the people is more, so its range is about 1.7 meter. If we are doing in Asian countries, the height of the people are generally less, so it's about 1.5 to 1.6 meters. So these are the effect of temperature. So operative temperatures, it combined dry bulb temperature and mean radiant temperature. But if we consider the equivalent temperature, then it also, in addition to dry bulb temperature and mean radiant temperature, it also considers air velocity. So air velocity has profound effect on the thermal sensation. So you'll see in next slide. See, if there is no wind, that at same dry bulb temperature and mean radiant temperature, if a person may feel comfortable, but as the wind starts, he may feel cold. So this is generally the difference between operative and equivalent temperature, and these are the actually derived thermal indices. So these are, so we, like, you combine two parameters or three parameters to get this, so they are called derived temperature units. This is the example of clothing. So if you are in casual clothing and just at home, you are close to 0.5 kilo. And if you are in snowy place, your clothing level is from 1.8 to 3. Or if you are in, Antarctic kind of place, it's greater than 3.5. So your layer of clothing is high. So these values are defined in a standard and we take from there. So science, actually the science behind this comfort is, is generally the balance between heat produced and heat lost. So if the amount of heat produced is equal to the heat lost, then we say that, okay, it's neutral. The body is not gaining heat, means like storing heat. So we, like, what is produced is that is lost, so body remain constant. So that is where we feel comfortable. So amount of heat your body is producing and that is lost to the environment, so you say that you are neutral. Whenever there is some kind of storage takes place or there is more loss compared to what you are producing, then, or more rapidly the loss is there, so we feel cold. This is the equations that we deal with in thermal comfort, that is a heat balance equation. So S is the rate of heat storage of human body, and M stands for metabolic, W stands for mechanical work that is done, that is met, and E is the rate of total evaporation loss, and R plus C is dry heat exchange through radiation and convections. So I'm not going into detail, but this is the general concept. And this is the heat loss and heat gain mechanism. It's convection, conduction, radiation. So conduction, convection, radiation, both here sensible, and evaporation is latent. So this you all know this. So what is the context actually? Why we do this research? Because it is indirectly related to energy. So you see this Indian basket of final energy consumption, that is 219.20. These figures are provisional. So you see that industry consumes around 68% of the total energy, and residential they consume about 11%. And again, if you see this next slide, it's much worrying, because in residential sector 60% of this energy consumption goes to air conditioning. So it tells us the picture that we have to think about it, and we have to construct our houses more responsibly so that we can minimize the energy consumption and enhance the comfort. So what is the research that I did so far? So my research starts with bioclimatic classification of Northeast India, because when we look at this figure, on the left hand side, you find that there is some kind of anomaly, and when we do thermal comfort research in residential buildings, we must have a correct information on about the bioclimatic zones. So because the bioclimatic zones has a lot of impact on the architecture, the way we design our buildings, the materials we use, and the way we provide the windows, the doors, and that means ventilation provisions. So these are the things that impact. So a designer must have a correct information about the bioclimatic zone. So we collected the data from the stations throughout the Northeast India, and we collected the information about temperature profile, humidity profile, precipitation profile, and altitude, and then we analyzed this data. These are about 30 years average data, and we analyze it, and finally we come to this. So we classified this Northeast India into mainly three bioclimatic zones, that is warm and humid, cool and humid, and cold and cloudy. And the right hand side figure, it represents the new bioclimatic zoning. So these are the ranges, the specific range, that summer and winter temperatures, that humidity, rainfall, sky condition, wind direction, and vegetation. So this provides more detailed information, and this information can be used by architects in designing the buildings. And also researchers who are working in this area, they can use this information. So we also have to do is to estimate the bioclimatic potential. That means the climatic features that we can use in the building to enhance the comfort and lower the energy consumption to attain the comfort. So this analysis is also done, and this is the potential. So in summer, we know that in summer we have a cooling requirement. So how much cooling we can achieve naturally, we can see in this table. So in warm and humid, in summer months, we can get we can use natural ventilation at about 16.6% of the time. Cool and humid, we can also have the same potential. Passive solar cooling in cold and cloudy bioclimatic zone, we can use it 22.5% of the time, and so on. So we also see the comfort duration, where we don't need either, we don't need cooling. So naturally we are comfortable. The temperature lies between comfortable range. Same as for heating. So we also studied the existing features, in traditional architecture. So we find that there are a lot of bioclimatic features in traditional architecture related to ventilation. These features, they enhance natural air circulation inside the building, as there are a lot of openings provided, and these openings are according to the wind direction. And also to minimize the heat gain, the structures are made of wooden structures on the top floor, and a lot of wood is used. So these are some of the solar passive features about ventilation techniques we got and we documented. This is the shading we found in the buildings that are more than 70 years old. This is the architecture of Cherapunji, where it slides in cold and cloudy climate, and see the compactness and use of locally available material, that is the stone blocks they used to construct the houses. And we can also see the chimney, that is the and that is the heating source that is used to heat the uh, indoor environment. So next is thermal comfort and thermal performance study. So we carried out survey in around 150 houses, 50 houses in each climatic zone, and we interacted about two occupants in each houses. And this study is done throughout the year, and then we evaluated the data. And also we selected 3 houses in this one in each climatic zone, and we monitored them for almost 1 month in each season. That is 4 seasons in a year. That is if we start with winter, spring, summer, and autumn, and then we carried out the thermal performance study. So this is the statistics of the thermal comfort survey. And this is about the neutral temperature. So warm and humid has a neutral temperature of 26 degree, cool and humid has 24, and cold and cloudy has 22. Same information is represented by this figure on the right hand side bottom. And this is about the comfort range that we found after analyzing the data. For warm and humid climate, that is Tezpur. Tezpur is the study location, and it lies in warm and humid climate. So we found that the comfort range, it starts from 22.8 and it goes up to 29.1. So this is about almost close to 7 degrees Celsius. So now with this range, if we provide this information to the architect or a building designer, he can design the building, and that is responsible in response to the climate. Same is for Imphal and Cherapunji, and in all the places we got the comfort range throughout the year. It's close to around 7 to 8 degrees Celsius. And it was a quite interesting information that when we communicated, it got published in Building and Environment. And from there onwards, the people starts talking about the range of comfort temperature. So, it's always not possible to monitor all the houses or visit all the houses in a particular region, because there is a time constraint, resource constraint, and also accessibility. So it's always beneficial, or when if we do some kind of mathematical modeling. So and here we did the mathematical modeling using the multiple regression technique, and here we can predict the indoor temperature of the similar of the houses that are constructed in a using similar material. They have similar built up area, similar window to wall ratio. So if this is and we know that in a particular area around most of the houses they are designed in a similar fashion. So if we monitor one house, then we developed and we use this technique, then it becomes easy to predict the indoor temperature in most of the houses, and its accuracy is almost close to 95%. So and it is very beneficial for detailed study. So we worked with Professor Givoni, and now he is no more, but he is a very renowned figure in bioclimatic study, and he developed this technique, and I learned from him this technique. And see the validation. So overall correlation coefficient is almost 0.96. That means almost 96% of the variations these relations explain. So this is quite high in terms of accuracy, and this technique is very efficient. So now similar techniques are being developed using artificial intelligence, neural network, and Python programming language. But see, the high reliability we can achieve through this just Excel programming, Excel sheet programming. So now again, also, it's not possible for us to do experiments in different conditions. We cannot, sometimes we cannot create some conditions in the during the experiments. So it's always better to do the simulations. So the most efficient simulation tool in this study, in this area of research, is Transys. There are other tools also, like Design Builder, Energy Plus, Virtual Environment. There are a lot of tools, but Transys has got some special capability because it's a very modular program. So whatever you want to do, you can do. There is as such no boundary. So, and it's very versatile. So this tool is used very widely in building energy simulation. So we also studied, and we tried to integrate the occupant behavior. This, like, occupant behavior has a profound effect on energy consumption in the building, because if the person is uncomfortable, so he will take all the actions. That is his and these actions will all is focused in restoring the comfort. So, and also each occupant has different behavior. Sometimes, like, if people will just enter in the house and just his metabolic activity is high, so he will just open the window and let fresh air come in. Or sometimes he will not open, he will just switch on the fan. So all these behaviors, it's very difficult to integrate in the simulation tool, and but we tried. And these all behaviors, we we got it from the data after analysis. So this data we collected in the thermal comfort survey, we analyzed it, and we got this occupant behaviors, and we tried to integrate it in building simulation tool. So this is the house where we modeled in Transys, and we try to integrate the occupant behavior there. So this occupant behavior is related to the opening and closing of window. So we have control strategy 1 and control strategy 2. The control strategy 1 is the strategy that we got after analyzing the thermal comfort data, and control strategy 2 we just devised just to check how effective is that the control strategies. So we just created our own strategy 2, and we compared the results. So this is about the swing in the temperature. So what is the difference in the temperature it creates through control strategy 1 and control strategy 2? So the middle of the x-axis is the summer month. So it's all in hours. So in 1 year we have 8760 hours. So all is in the middle of the x-axis represents the summer month. So we see that control strategy 1 leads to the decrease in the temperature, but control strategy 2 leads in the temperature buildup, leads to the temperature buildup in summer month. So this we get information from here, but this information is it's like it's hiding the detailed information that what is the monthly impact. So we carried out another analysis. So we calculated what is the number of comfort hours in each month. So here we see that control strategy 1, in control strategy 1, the comfort duration improves even in summer. But because of control strategy 2, it deteriorates in summer, and same in winter also. So this from here we made the conclusion that the occupants of the houses, they are operating the windows quite wisely. So when we design automation of the window opening and closing, we must have to do some kind of surveys in the houses so that we can devise the exact control strategy. So, and also we know the effect of cool roof. Cool roof is a passive technique where we do reflective coating on the roof, the exposed part of the roof, and then we analyze the effect of it on the indoor temperature. So that is called these days we you should be hearing a lot about reflective coatings, cool roof techniques. These are nothing but the reflective coating. That is a white paint. It's generally white in color. It has a high reflection coefficient, and then it reflects most of the solar radiation. So it blocks the heat that transfers to the indoors. So we analyze that also. So for that, we considered a simple house, and we put all these parameters, and we run the simulation. And the figure on the bottom in the left hand side, you see the construction, how we constructed. So we put the roof slab, and above that we apply the white paint, and then we run the simulation. So here we find that when we apply the the cool roof concept, there is a temperature decrease of around 4 to 5 degrees Celsius in summer month. And if we convert this in terms of heat energy and in terms of cooling load, it is huge. So 4 to 5 degree lowering of temperature inside the building is very huge. So with this we found that cool roof is quite effective. So these are the other analysis. It shows about the heat flux, and here we also found that the heat flux almost there is a gap of around 5 to 6 hours. So this also very effective there. So when you have seen this, the definition is about adaptive thermal comfort. So there are always two approaches. One is as heat balance approach, and one is adaptive thermal comfort. And as the both definitions are different, so generally people they carry out experiments and in the heat balance approach, using heat balance approach, and when it is applied to the field, there is a deviation. So since that study should not get wasted, if we can add some kind of corrective term, in always in physics or in engineering, when we do some detailed experiment and and we find that there is some kind of error, some kind of deviation. So what we do, we we calculate some kind of coefficient and we add to the actual formulation so that it defines our deviation. It defines the deviation that we get in the experiment result. So same approach is applied here, and we calculated the adaptive coefficient. So this is the formula of that. Lambda is the adaptive coefficient, and we calculated this coefficient. When these coefficients are added to the actual formulation of the thermal comfort, the results become close to the field results. So this graph shows the same thing. So we see on the left hand side, top figure, left hand side, there is a deviation in AMV and PMV. PMV is the heat balance approach, and AMV is the adaptive approach. So when we applied the adaptive coefficient to this PMV, the results become very close to the actual experimental results. Same is for summer conditions. So, and I also, as sir told, that I also went to European country, that is Belgium. So where I was assigned to work on, the traditional residential buildings. These residential buildings are almost around 70 years old. They are constructed around after First World War, and I have to work on them, and I have to define that what is the comfort status, and why people are not going for retrofitting, because the heating energy consumption was one of the highest in those buildings. So, and even from the European standards, they are almost double, 2 times of that. And Liège city has almost 60% to 70% of the building stock that lies in that category. And also, since these houses are constructed during that time, there are no modern equipments for heating, and also there is nothing like insulation at that time. So these houses are already designed very compact. Now if people goes for refurbishment, means retrofitting, they lose a lot of space, because the insulation materials are anyway around 6 to 8 inches thick, and they lose a lot of space, indoor space, and they have a lot of other losses, like the loss of furnitures and everything. Now when they retrofit, it doesn't fit in the building, and these costs were not covered by government or bank. So there's a failure, and then I was assigned to do this work, and I completed it. And for that, I have to classify the building stock. What is the density of this building stock? So this is the Liège city. You see, it's a very beautiful city. And these are the type of buildings. So they have already classified the type of building, and based on the area, based on the exterior facade, and based on this, the exterior look. So they have classified the types, and so I took all the data from their social general survey, and then segregated the data, and I did all this classification. So this is the map of Liège city, and it is divided in 27 neighborhoods. And So neighborhoods, we can say that municipal wards, simply we can say that they are equivalent to municipal wards. And I calculated the density of these houses in different wards, and then after that I selected the highlighted ones, because in these wards, or neighborhoods, they have the highest density of these buildings. So you people are listening?
Yes, sir.
Yes,
Yes.
sir.
Yes. Yes. So, and then, so here, these are the statistics. So house having, the first figure is about the fuel consumption. So you see there's EU27 and Belgium, the energy consumption in the household, in the industry, and that is the comparative figure. And the CO2 emission, corresponding CO2 emission. And then the type of fuel they used in the household. And the last figure is the houses with, 2 facade, 3 facade, 4 facade. So exposed 4 facades means it's the individual houses. So 3 facade means there are 2 houses, they share one common wall. So there 3 exterior, these houses is like 3 sides are exposed to the, environment. And the houses with 2 facades, these are generally apartment houses. So this is again the figure, and then here is the age group of houses. These are the classification of the houses, and then age group in different, about the different build-up area. So, and then composition of external walls of the houses that are constructed before 1945. And this is the distribution of building with sheer facade, more than 35%. So you see that at the center, means center where the space constraint is there. So here there are more number of houses. They have, 2 facades are exposed to the outside environment. That means there are more apartment buildings. This is about density of apartment buildings. And there also I monitor 2 houses. So one in winter and one in spring, and see, this is the characteristics of the houses. So in winter, see, this temperature is quite fluctuating because these houses, in this house, thermostat is not installed, since it was the very old house. Its construction was close to 1918 or something. So, and also they control the heating manually. So, and they have also this, gas heating system. So they don't have radiators. So they burn gas, and through that gas burning, they heat the indoor temperature. So always they have. So this house this automatic this thermostat was not installed. So they are controlling the heating equipment manually. So you see this, there's a large fluctuation, and also there's a, see, in winter months they have an overheating problem. So it's like temperature is going close to the 30 °C. So this is one of the biggest problem in all European homes where there some kind of retrofit is done, and so even in winter months they have a overheating problem. And similarly, if we see in the spring months, spring season, this house has a thermostat installed, so heating equipment was controlled automatically. So thermostat was set, and then it varies between 18 to 22 °C. But at the around in April, there we see that the thermostat is switched off, and then the house is operated under the natural ventilation mode. But still in the end of May, we see that overheating problem, it's just popping up. in the. So this overheating problem in the European houses are very high these days, because the government has enforced this retrofitting. They have to go for insulation, and the houses are such that the top floor is the bedroom, and in Europe, the sunlight, uh, it starts at around morning 8 o'clock, and it in the evening it goes up to 8:30 p.m. Up to 8:30 p.m. there is a sun. So almost the entire day this room is exposed to the sun, and then there is overheating. So these kind of issues are cropping up, so they are working on the cooling technology, where the houses can be kept at comfortable temperature. So this seems to very strange, but yeah, this is the acute problem these days in all the European houses. So this is the detail about the comfort duration in these houses. So the pattern is quite distinct. So you see this. So temperature range and duration of various houses. This is also the adaptive actions that occupants take during the winter and spring season. So what they do, they switch on room heaters. They use portable room heaters. Though they all the houses, they have radiators, but still they use portable room heaters. So it says that the houses are not evenly heated. So they close window, they move window curtains, they wear warm clothing, they move to a different room, they sit away from the window, and also this lighting level is very low. The natural lighting level is very low, even during the daytime. So during the daytime itself, so they want much brighter indoors. So these are some of the problems, and that is what my findings were, and I submitted them. So now, since I'm still working on this area of thermal comfort, so I studied different types of built environment. So some cases I will discuss here, and here you will see some graphs, some plots that we commonly do in thermal comfort study. So this is about the offices. So I did this study in the thermal comfort status in the offices of Northeast India. So again, my study locations were Tezpur, Shillong, and Imphal. So in first leg of my studies, I consider Tezpur and Shillong, and I will see the analysis of this. So this is the way we do surveys. We also record the data. So we interact with the occupants one by one, and we take the environmental measurements, and then we analyze it. So the top left hand side figure is about comfort temperature. So if we draw the vertical line from the peak of the normal, so we see that the comfort temperature is about 27 degrees Celsius. So here also almost a similar result we get from the regression analysis. And the bottom left hand side, we see this general office setup in Northeast India. So they have open type, they have cubicle type, and then bottom right hand, extreme right figure, you see the range of comfort temperatures in the offices. So it starts from around 26 degree and it goes up to 29 degrees Celsius. These are again different curves that we used to. So here we also calculate neutral temperature. So for neutral temperature, we have to do Probit analysis. So again, if we do the probit analysis, we find that a neutral temperature is close to 24 degrees Celsius. Though neutral temperature is close to 24 degrees Celsius, but people prefer to be higher than that. So they prefer close to 26, 27 degrees Celsius. So because that is their comfort temperature. So people tend to stay like, warmer. So again, if we see the clothing relations, we find that it is not linear. And also you see this fan use. So you see this middle, the bottom figure, the x-axis is globe temperature and y-axis is proportion of fan use. So we see that at about 24 degrees Celsius, the fan starts operating, and when the temperature is around 32 to 33 degrees Celsius, almost around 70 to 75% fans are running. So this kind of analysis is done. So this kind of analysis is very important when we model, occupant behavior in the building energy simulations. This is about the academic. So we also did thermal comfort study in the classrooms. So this is the general setup. And we also try to define the comfort boundaries on psychometric chart, because here it gives us the range of the humidity and the temperature so this kind of plotting is very important. It also gives us the idea about where we need to go for conventional heating, dehumidification, and where we can use evaporative cooling technique, and also we go for air conditioning. We have to go for air conditioning. So this kind of boundaries are defined on this, and then if you do the plotting, uh, we can create this kind of boundaries for our study region. So generally, for reference, we use ASRE defined boundaries, but most of the time they are not accurate, because for that boundaries, actually, the European samples are considered. But now, since we are doing the study on Indian subjects, so we have to define our own comfort boundaries. So here we did. So this is the bioclimatic comfort chart for composite climate of India. So these boundaries you see on the right hand figure. So this is defined. This is defined based on the data we collected. And this kind of chart is very important for architects. So, and also building designers. So we can use the solar passive features or bioclimatic features. We can integrate them in the building design. This is also the similar kind of plot where we defined the comfort zone, and then we did the analysis of fan use, and people who want cooler, people who want warmer, and then this kind of analysis. So we find here for composite climate, the neutral temperature is about 26.4 degrees Celsius. This is also the type of clothing characteristics. So again, here we find that the clothing insulation is a non-linear function of temperature. It's not directly related to the temperature. Sometimes even if temperature is higher, people tend to wear high clothing because there are cultural and societal compulsions. This is about the number of studies still that are being done in classrooms, and where like it's a temperate climate, tropical and subtropical climate, then Mediterranean climate, hot and dry climate. This shows the how many studies are done at primary school, secondary school, and university level. This is the process with which we derive the adaptive comfort relation. So this is regression analysis. So in this, we found that the occupants who are at university level, that means university level students, they are most sensitive to the change in temperature, and the students who are at primary school, so they are less sensitive to the change in temperature. This is about the higher and lower limit of comfort temperature. So Asia has the higher range of comfort temperature because in Asia most of the schools are still the classrooms are still naturally ventilated. So this is about the study of thermal comfort in industrial buildings. This is again, these are the probability curves. It tells about the adaptation. The left hand side figure, it tells about, and this you remember, it's similar to the hysteresis curve. The separation of these two lines, it says that this much temperature change needed for an occupant to change his preference vote. So if this you see this, if you consider at the 60%, you see this temperature is about, here it's 22.5 to here is say about 32.5, so almost 10 degree. So he has from neutral, he has 5 degree on the cooler side, warmer side, and 5 degree on the cooler side. So almost there is a span of 10 degree. So the person, you see this right hand side figure, it says the same information represented in a different way. So this the two green line and the temperature in between that, it tells about the range of comfort temperatures in the industrial setting. And again, this is the different types of analysis where we define the comfort range on the left hand side, and then on the right hand side is the logistic regression analysis for predicting the fan use behavior in the industrial setting. So you see that in the industrial setting, the fans are starting way below 20 degrees Celsius. Close to about 18, the fans it starts operating, and when it reaches about 30 degrees Celsius, almost 80% of the fans are operating. And when it is about 35 degrees Celsius, almost 100% fans are operating. Since this is the industrial setting where the activity level is very high, the people has to do very hard work. So their metabolic activity. Yes, this you see this the right hand side figure. It tells about the probability of phone use and the temperature. We see that at industrial setting, the fan use starts at close to 18 degrees Celsius, and it goes up to around 80% fan use at about 30 degrees Celsius, and at around 35 degrees Celsius, it's about 100%. So we see that at industrial settings, since activity level is very high, there is a lot of heat production, and then people prefer higher air velocity because the cooling effect is more because of evaporative heat loss. And then it's the relation between outdoor temperature and clothing. So we see that this relation is again non-linear. So, and this is about the use of face masks. So this study is done at the time of COVID. So we also asked the factory workers that what are the difficulty they are facing when they apply mask on their face. So they say that it is irritating, they feel suffocating, also bad odors, and they face difficulties in doing work. And there are others listed. They some of them they reported the combined effect. So this is about our research. It's got listed in the ASRE Comfort 2017 database. So now it's a very good news for us that the research what we did is now part of the standard. So about the future of thermal comfort research. So now the thermal comfort is the thermal comfort research is moving towards personalized thermal comfort in the offices and other built environments to increase the productivity. This research is also moving towards linking occupant behavior in building simulations uh, because it has impact on the energy consumption, and also impact of climate change and changing weather patterns on present and future thermal comfort requirements of the occupant, and then the impact of climate change and changing weather patterns on human well-being. And it's also about building energy simulation and building model calibration procedures are not standardized. So there are a lot of research is going on to standardize this process because this will help in evaluating the results. And this is about collaboration, and these are about publications. So this study has resulted in this much publications. And this is the end of the lecture. Thank you for your patience.